predicting waiting time when we have one server. If we are now sure that our arrival and service distributions are appropriate, meaning that both arrival and service are stationary processes and at inter-arrival times are exponentially distributed, we can start talking about a model that will predict the waiting time for a single server that processes some arriving units. So the system we will be discussing will have one server depicted by this rectangle. If there is a customer in this, being served by the server, we will say that there is one unit. This dot here represents a unit being processed by the server. So there will be some inventory here, IP, right? And then there is a waiting line in front of the server. If customers are waiting, let's say they called and they are now on hold listening to some music played over the phone, then they will be represented by dots here in this triangle. So the flow here is that customers, when they call, they arrive through the buffer, and the moment the server becomes available, the first customer in the waiting line moves to the server, and once the service is finished, the customer leaves. So there is entry, the beginning of the service, and then departure. And if you think about the times, we can say that the time spent in this buffer is the waiting time. The symbol will be TQ, and this will be service time, P. And most symbols here will use either Q or P as index to indicate whether we are talking about the inventory or the time in the waiting line in the queue or in the process in the server. And of course, flow time will be T, a total of waiting time and the processing time or service time. Also note that there is a flow rate through this system. The same flow rate will apply to the buffer as to the server, because we're assuming all customers are patient. Everybody who calls goes through the buffer, perhaps immediately goes to the service and then leaves the system. But the flow rate through this system is one flow rate R. So the parameters of the model we will have are average inter-arrival time, A, and average service time, P. We will also have coefficients of variation, CVA and CVP, corresponding to inter-arrival time and service time. So of course, we need to know something about standard deviation, not just average or mean inter-arrival and service times. We will also calculate the utilization. We can calculate utilization as flow rate over capacity. And notice that the flow rate is 1 over A. If there is one arrival per A time units, then this will be the flow rate, 1 over A. And the capacity, given that we have one server, will be one customer per P time units. So the capacity is 1 over P, and therefore utilization can be calculated as P over A, time to serve, divided by average inter-arrival time. Flow time can be calculated as waiting time plus service time, which we already said in the previous slide, TQ plus P. Inventory can be calculated as the sum of inventory in the queue and in the process, IQ plus IP, right? These are average number of units in the waiting line and average number of units in the server. Notice average number of units in the server is not necessarily 1, because, right, it could be that at some moments there is no customer, so the average IP would usually be somewhere between 0 and 1, a fraction. And the waiting time, this is the main formula of our model, will be calculated as a product of 3 terms. We will multiply service time, which is P, by a utilization factor that you see here, U divided by 1 minus U, and then we will multiply the result by the variability factor, which takes 2 coefficients of variations, arrival and service, inter-arrival and service time coefficients of variations, squares each of them, adds them together, and divides them by 2. This requires, of course, a stationary process. And it also requires, a very important assumption is that U must be less than 1, meaning that the utilization should be less than or 1, or implied utilization should be less than 1. So the system only works correctly, or this waiting time formula, the model works correctly only if utilization is less than 1. If you have utilization 100% or implied utilization more than 1, then in fact the waiting time predicted by this model, you could say, it goes to infinity. And the reason for this is that if your implied utilization is higher than 1, it means that you have more demand than you can cope for. And because we're assuming in this system that no customer ever gives up, all customers are patiently waiting for service, and the time horizon in our model is infinite, then what we have is that as the system is processing customers, there is on average more and more customers accumulating in the waiting line, and so the inventory of customers who are waiting will be increasing to infinity, and also their average time will not be limited from above by anything, so it will also increase to infinity. So if we satisfy these restrictions, the average waiting time, notice it will grow with service time. So the higher the service time, the larger the service time, the larger the waiting time. But notice it is not linear because P is also hidden in the utilization factor. And this utilization factor, it is calculated based on P. So, so the growth of the TQ when you increase P is not linear, right? Also, the waiting time will grow, of course, with utilization factor. And notice that when the utilization factor, when utilization is very close to 1, this utilization factor will be very large. So I invite you to, let's say, calculate if utilization is 50%, this will be 0.5 divided by 1 minus 0.5. So it will be half in the denominator, half in the numerator. The utilization factor will be 1. What if utilization is 90%? It will be 0.9 divided by 1 minus 0.9, which means it will be 0.9 divided by 0.1. So the utilization factor will be 9. So from 1 at 50%, the utilization factor increases to 9 at 90%. And if you increase, let's say, utilization to 99%, it will be 0.99 divided by 1 minus 0.99, which is 100th in the denominator. So the utilization factor becomes 99. And so the waiting time, right, will increase, right? With the utilization 50%, this was a factor of 1. With 99% utilization, this factor is 99. So it is really a huge growth of the average waiting time. All of these are, of course, averages, average waiting time, average service time, and so on. And of course, the waiting time will also grow with variability. The larger the coefficients of variation, the more variability, and of course, the larger the TQ will be. Consider the following example where we want to predict the waiting time. We have a call center where customers arrive randomly and independently, and roughly we have 3 calls arriving every 15 minutes. And the service time on average is 90 seconds with a standard deviation 120 seconds, right? So we would like to know all the measures like inventory flow time and flow rate. In particular, we would like to know the average waiting time. So what do we know here? Well, first of all, we need to define what the average time between arrivals is. And the average time between arrivals can be calculated as 15 minutes, right, divided by 3 calls. So this is going to be 15 minutes divided by 3 calls, which is going to be equal to 5 minutes. I'm going to convert this to seconds because the service times are in seconds. And this is another important comment. Keep all the time units uniform. So 5 minutes will be 5 times 60. That will be 300 seconds, right? What else do we know? We know that processing time P is 90 seconds. So maybe I'll put it seconds, right? And we will also know that the standard deviation of the processing time is 120 seconds. Now, we need to calculate coefficient of variation for interarrivals, and assuming that these are random independent arrivals, right, we would know this is an exponential distribution, right? So assuming the process is stationary and exponential, and interarrival times are exponential, coefficient of variation should be 1, right? So assuming exponential interarrival times, and also coefficient of variation for the service time, we can calculate it because we're given, right, 120 divided by 90. 120 is the standard deviation divided by mean 90. It will be 1.333, right? Again, I'm assuming both of those are stationary processes. So now I am ready to calculate the utilization, and this is important, right? Remember, utilization is average processing time divided by average interarrival time. And this is because I have one server, so I can do the calculation as 90 divided by 300, which will be 0.3. And the important thing is it's less than 1, so the model will work or can be used, right? If it wasn't less than 1, we wouldn't be able to use. And in fact, this is implied utilization if you want to be strict. But of course, if it has to be less than 1, implied utilization and utilization are the same thing. So now I'm ready to calculate TQ. And if you recall, right, the formula is this. So let me just move it here. Equals, right? And so I will do the calculation. Let me again copy it. And then replace values. So P is 90. And of course, it is 90 seconds. Then that means the TQ, the waiting time, will also be expressed in seconds. Utilization is 0.3 divided by 1 minus 0.3. And coefficient of variation are 1 squared. And coefficient of variation for P is 1.333 squared, right? So this, we need to calculate exactly, and let's not forget, yeah, the division by 2 is here already. So if we do the calculation, right, let's actually see this. So this is going to be 0.3 divided by 0.7. So the utilization factor is actually quite small. It's a fraction, roughly half, right? And then this is, notice when the coefficients of variations are both 1, if this was 1, then it would be 1 square plus 1 square, meaning 2, and divided by 2, it would be 1. So the variability factor would be exactly 1, not increasing or decreasing, but because it is 1.33 squared, it will be somewhat larger than 1. If you do the calculation completely, you will discover that the result is 53.57 seconds. So what we have here is that the customers will be waiting on average somewhat less than 1 minute, right? This is average waiting time, remember. So one question here, is it possible that a customer waits 2 or 3 or 5 minutes? It is in fact very likely that there will be customers waiting more than 2 minutes, because remember, in a queuing system, there is a lot of randomness. When there is a lot of variability, it's very likely there will be some customers who will be waiting 0 seconds. And therefore, if you want to have an average of 53 with some values being 0, some of them must be more than 53.57 seconds. And very likely that there will be maybe a small percentage of customers who will be waiting 2, 3, 4, maybe even 5 minutes. So now that we have average waiting time, we can actually calculate other measures, like we can calculate the flow time, TQ, plus processing time, or how much, right? On average, the customers spend 90 seconds in the service and 53.57 seconds waiting. So we can calculate a total, right? 53.57 57 plus 90, that's 143.57 seconds, right? So we have the average flow time. The flow rate, of course, is 1 over A, right? So this is the same actually as arrival rate, 1 over 300 customers per second, right? Units or customers per second. And then we can also calculate all the other measures. We have the flow times, we have the flow rate, so we can also calculate inventories, right? So inventory will be R times T, right? So that will be 143.57, or actually that's T. R is 1 over 300 times, right? Time 1 over 300 times 100 times 143, right? So this is going to be 0.479 units. So I noticed that the number of customers in the system, including waiting in the line or being served, on average, there will be less than half a customer. One needs to keep this fractional. Also, we can calculate inventory in process on the server, right? This is going to be R times processing time, flow time, and the process is P, right? So again, we can calculate this the same, right? The same flow rate, 1 over 300 multiplied by 90 seconds, right? So this is going to be equal to 0.3 units. And this is actually not surprising, right? On average, there will be 0.3 units being served, and it's exactly the same as utilization. There is a probability that 1 unit is on the server is exactly equal to utilization, and probability that 0 units are on the server is 0.7, 70% chance, 1 minus utilization. So average number of units should be 0.3 units on the server, right? And we can also calculate how many units will be in the queue the same way, either by subtracting I minus IP, right? Just by doing the calculation of the inventory, or we can, right, which will be 0.479 minus 0.3, which will give us 0.179 units. So on average, there will be so many units. Let's call these units, but of course, these are customers, right? So there will be on average a fraction of a customer, 0.179 customer waiting, right? And we could also use the formula IQ. For the IQ, we can use the Little's law formula, flow rate times time in the queue, right? And we should also get exactly the same result if we do this, also the same number of units.